Everyone. This is the Steel 2 lecture in which we're going to discuss long-span truss structures made of steel. So the emphasis in these case studies will be buildings with long-span steel structures and to examine how the structure, services, and envelopes of the building are integrated with the construction systems or through the construction systems to achieve a highly integrated architecture. So these are not standard steel-framed buildings in which the steel structure gets clad and hidden away inside and out. Instead, these are buildings in which the structure and services are fully expressed in the completed buildings. They're highly visible. So these buildings have some things in common. A number of things in common. They're all long-span steel structures made of steel trusses, and they are all tubes of space that are linear and open-ended. The steel is the primary structure in each of these buildings. Some buildings use standard steel sections, principally tubes, circular tubes, and others use cast steel components. Each of these buildings relies heavily on prefabrication and factory production. This should not be confused with mass production of standard steel components. So each of these buildings has a custom fabricated steel structure, and each building has a high quality of design and an obsessive attention to detail. For each of these buildings, the construction process and sequence has shaped the architecture of the buildings. And finally, each of these buildings is a public building that explores new concepts of the image of a public institution in a democratic society. So technology here is not an end in itself, but a means to achieve wider social goals. These buildings are not merely the result of technical decisions, but also reflect social and cultural ambitions. So those are the similarities among the buildings. The buildings are quite different as well. They have differences. So each building has a unique structure and a unique structural concept. Each has a different relationship between structure and skin. If we think about a continuum with standard steel sections at one end and custom steel sections at the other, each building finds itself at a different place on this continuum. And finally, the resulting aesthetic of the buildings is very different. This ranges from extremely expressive, or what you might call a Baroque sensibility, to extremely restrained or classical sensibility. So I would like to look at the buildings in the order of their completion, that is historically from the earliest to the most recent. The architects involved all knew one another well at the time and still know one another well, and they even worked together on different projects. And many people who worked in their offices worked first for one and then the other, so ideas traveled from building to building. So the first of these buildings is the Centre Pompidou in Paris, or the Pompidou Center. And this was designed by architects Renzo Piano and Richard Rogers. And so these should be familiar names to you. This is the only project that Piano and Rogers ever did together. And so when this building was completed, they split up and formed their own practices, and they both went on to become very accomplished and famous architects. The engineers for this project, for both structure and services, were again Arab. So these are the same engineers that we saw for the San Francisco Federal Building. So the client for this building was the French government. The French government has historically been a great patron of architectural projects. They see architecture as a projection of the image of the state. And they sponsored an open international competition in 1971 in which there were nearly 700 entries. And Piano and Rogers won the competition together with the engineer from Arabs, a young engineer named Peter Rice, who Piano continued to work with throughout his career. Piano and Rogers are both very well known now. They're world famous, but at the time they were young architects in their 30s. Each had done a few small projects, but nothing of any kind of scale or significance. And they won this open design competition. So they won it in 1971, and the building was completed 6 years later in 1977. The engineer was in his late 20s. His name, as I said, was Peter Rice, and he said at the time, he said, quote, "We did not expect to win the competition, and therefore we explored ideas in our entry without caution, without compromise. At the time of the competition, we were not interested in technical solutions, but in firing the imagination." It is certainly a building that was designed by young and spirited architects and engineers who were willing to take many risks. So on the left is the competition model that they submitted at the time, and on the right is the completed building. And you can see that the completed building remains very faithful to the idea of the competition scheme, very close to the original idea. The program for a building is a hybrid program, which is very normal now, but it was quite radical at the time. And so it is a hybrid of many cultural institutions. It contains, all of these are in the plural, by the way, art museums, cinemas, restaurants, theaters, design centers, and libraries. It is a big, loose fit box in which anything can happen. It was very much a product of the liberating 60s. It was conceived as a popular palace of culture in which people would not feel intimidated. So if you think about the Metropolitan Museum in New York City with its imposing classical facade and its great big flight of stairs leading up to the entrance, this is monumental and intimidating. So they wanted to be anti-monumental and very open to people. This is the section that they submitted with the competition. And the structure of the building is clear spanning. So you can see to the left and the right hand side of the structure, there's a column at each edge of the building. And the distance between these columns is 140 feet of column-free space. So it's a clear spanning structure that spans 140 feet. This produces on each floor of the building 2 football fields of column-free space. So it's a very large building. And you can see in the structure, in the section, that there are multiple levels of accommodation below the ground. So these are mechanical plant rooms and underground parking. There are about 5 basements. And then above ground, there are 6 floors of accommodation. But each of these floors is double height, 21 feet floor to floor. And so basically, this is a 12-story tall building. The substructure of the building in the ground is site cast concrete, and the superstructure above ground is steel. So within this column-free space, the idea is that any program could be anywhere at any time, and programs could move around over the life of the building. Then you see outside the column on each side of the building, so on the front of the building, on the right-hand side of the section, you can see a narrow zone, and this is dedicated to the horizontal and vertical circulation of people. So the circle and the tube that you see are the corridors and the escalators that enable people to move horizontally and vertically through the building. The narrow zone on the left-hand side of the section at the rear of the building is dedicated to the vertical and horizontal distribution of mechanical services. And so this very simple plan diagram then emerges of this 140-foot clear span of column-free space in the middle, with then the circulation zone for people on the right-hand side of the plan drawing and the circulation zone for mechanical services on the left. So following the competition then, this is a more refined drawing of the building. The only thing I would point out here is that it is a bit misleading because the bottom of the drawing, for some reason, has been cropped. And so it shows only 1 basement, but there are in fact 5 basement levels under the building. And so you see the concrete substructure and you see the steel superstructure above ground, the column-free zone in the middle of the plan, with then the human circulation zone on the front of the building to the right, and the mechanical services circulation zone at the rear of the building on the left. And so as the scheme developed and becomes more refined, they then build more refined models and do more refined drawings. And so the image at the top is the front face of the building, the model of the front face of the building, with the horizontal corridors on the face of the building and the escalators that carry people floor to floor. On the rear of the building, in the bottom image, you see the vertical and horizontal distribution of mechanical services, which are color-coded. And these are expressed exactly like this in the completed building. They're not going to be covered up by anything. So the first decision that the design team made was that they wanted to use cast steel for the structure. They didn't have a structural principle in mind, but they decided that they wanted to use cast steel. And this was because they decided that hot rolled sections, like the wide flange sections that you see here, are the same the world over. They lack character, lack personality, lack individuality. And so they decided that this was not the kind of steel component that they wanted to use. They, however, were very interested in 19th century cast iron buildings like the Crystal Palace that you see here and the great Victorian railway stations, which were all cast iron. And these cast iron structures had a great deal of character and were very beautiful in their terms. But cast iron declined in use because it had a serious problem. It was brittle. And so they wanted to use cast steel, and to overcome the problem of brittleness, they looked to new alloys that had been developed in the 20th century to deal with extreme structural stresses like North Sea oil platforms or nuclear reactors. So they married this new knowledge of fracture technology and alloying to the 19th century casting craft to achieve their steel structure. So they're both backward-looking and forward-looking. The structural concept for the building is represented in this image. It is the principle of the tied cantilever. So this was developed by a German bridge engineer named Heinrich Gerber, like Gerber's baby foods or Gerber's baby foods. So the line of his thinking goes like this. If I'm building a 3-span bridge, if you look at the structure in line A, the easiest way to build it is to have 3 separate beams making the spans. This makes it easy to construct. But the disadvantage of this is that it maximizes the bending because there's no continuity in the structure from span to span. So in line B, if I want to minimize the bending of the structural components, then the best thing to do would be to build the bridge with one continuous element over the 3 spans. So this minimizes the bending, but it's extremely difficult to build. So his approach, which is seen in line C, is to have 2 simple spans at each end of the bridge, which you see, and then extending into the middle bay on each of those spans is a short cantilever. And that cantilever then gets weighed down by the element making the middle span. So the middle element loads the end of the cantilever, which pushes it down, which reduces the bending in the 2 end bays. So they take this idea for the Pompidou Center, and their cantilevers are not in the middle of the building. They actually turn this idea inside out and put the cantilevers on the outer ends of the building. In the Pompidou Center, then, there is a grammar of structural components. Anything that's working principally in compression is a hollow steel tube. Anything that's working principally in tension is a solid steel rod. And the complex joints are all steel castings. So with this grammar in mind, there are 4 primary structural components which you see in the drawing at the bottom left. So the first is the column, which is working principally in compression. So this is a steel tube. And the steel tube over the 12-story height of the building comes in 3 pieces. And as it descends from the top of the building to the foundation, the outer diameter of the tube remains constant, but the wall of the tube thickens as the structural loads increase on the column. So all of that now is hidden within this constant external diameter. We don't see the thickening of the wall. It's not expressed So this is very different than, say, the Exeter Library by Lewis Kahn, where he expresses that increased load as the floors of the building descend to the ground. So we have the column as the first structural component. Then the second structural component is the tension tie down, which you see at the extreme right of the drawing. And this is a solid steel rod. And just to give you a sense of the scale of this building, that solid steel rod is 9 inches in diameter. So it's not just rebar, it's a very hefty, solid rod of steel. The third structural component are the floor trusses. The top chords of the trusses are working principally in compression, and so those are steel tubes, and the bottom chord is working in tension, so those are steel rods. And all of the joints for the truss, which are rather complicated and organic shapes, are steel castings. So the trusses are 9 feet deep over this 140-foot clear span. And the top chords and the bottom chords are double, and then the diagonals fit, obviously, between those double members. The fourth structural component is the tied cantilever. And this, you can see, is the element that is threaded down over the top of the column, and it is connected to the column by a steel pin. And it then extends out, it cantilevers out, and as it does so, it tapers to a very thin edge to lighten the cantilever and to reflect the structural forces at work. And so here you see a model made by students showing these 4 structural components. You see the columns. The gerberettes have been threaded down over the top of the columns and pinned to the columns. The outer end of the gerberet is connected to the tension tie-down rod, and then the floor trusses, which span clear 140 feet. And in this image, you see the plan and elevation of the gerberet, and also the model photograph showing the gerberet. And so the gerberet is highly expressive in its shape. These are detailed drawings of the gerberet from top to bottom, plan, elevation, and a series of sections. And so you can see that the gerberet is very sculptural in its form. It is very bone-like, and where it's working hardest and where it joins another element, it fattens out. It's the same thing as our bones in our human body, our knuckles, our elbows, our knees. So it is very anthropomorphic, as I previously mentioned. So the steel structure of the building is a very significant piece of the building in cost terms, and so the bidding for this package of the contract was very fierce. And there was there's a very powerful political story here. Power politics played a role. So the bid for the steelwork was rigged, and on the day before the bids were due, all of the non-French contractors withdrew from the bidding process together, and the French contractors all said that the structure could not be built as designed. They changed the structural scheme and then overbid by 50%. So this is not a nice phone call to get if you are the architect. The bid was declared null and void, and the design team had to scurry around the world to try to find a way of getting the structure that they had designed built. So they looked all the way around the world, and Japanese steel fabricators said that they could fabricate the structure as designed in Japan and deliver it to site for half the budget. So this really concentrated the minds of the European steel contractors. And eventually the contract was awarded to a German firm called Krups, who said that they could deliver the structure as designed, on cost and on program. And even this appointment was very controversial. Um, France and Germany had fought one another in World War II, and Krupp had been a major manufacturer in Germany during the war, very deeply involved in the manufacture of weapons and ornament and uh, for the war. And so there was a lot of resentment that the Krups won the contract, but nonetheless they did. So the moral of the story here is that architecture is not simply conceptual or aesthetic. It is also deeply embedded in politics and economics, and sometimes, often, is influenced by factors over which we have no control. And so the construction sequence here then is that the site cast concrete substructure is being built on site. And so in this image, you see the excavation of the 5-story deep basement and the construction of the site cast concrete substructure. And this is a slow and painstaking process, which takes a little over 2 years just to construct the basements of the building. And while this is being done, then the steel elements are being cast and prefabricated in Germany. So the programs overlap to save time. And so you can see here then the scale of the castings. The gerberettes are not small elements. They're more like dinosaur bones, really, than human bones. Each gerberet is 25 feet long. That's about the width of Crosby 301. And so these are substantial elements indeed. So all of this was being done while the wet concrete work was being done on site. When they submitted the project for building regulations approval, the French authorities were very uneasy about using cast steel because of the history of brittleness of cast iron. So they eventually approved the use of cast steel with the condition that all the cast elements had to be load tested at the factory prior to their delivery to site to ensure their strength and integrity. So the steel castings have been in process for nearly 2 years. They were nearly all completed, and the factory testing began. All of the elements that were tested failed at half the required load. They were brittle. And so this is a complete disaster. What does the design team do? Do you require the prefabricator to make them all again and delay the contract for 2 years? This is a very expensive way to solve the problem. And so they looked for other alternatives, and they hired a specialist to try to find out what had gone wrong. What they discovered was that the fabricator, Krups, had not used the alloy that was specified in the contract. And so again, what do you say? Do it again and use the correct alloy and take your time. We can hang around for 2 years waiting while you do this all again. Or uh, or not. And so what they discovered happily was that the problem could be overcome simply by reheating the elements, not to melting point, but reheating them. This is a common procedure when working with metal called annealing. And what it does is it realigns the molecules and takes away the brittleness. So they were able to solve the problem without recasting. In these images, you see the castings for the trusses, for the diagonal connections of the trusses, and then the end connections of the trusses. The trusses were entirely prefabricated and assembled in Germany. They were transported to site from Germany to Paris by train, by rail, and then they were transported from the train station to the building site on specially designed trucks at night so as to minimize the disruption of traffic in Paris. So they came to the site as a single piece, 150 feet long, 140 feet long. So the construction of the steel superstructure, which is 75% of the volume of the building compared to the basements, only took 9 months. So the basements took 2 years. They're a very small part of the building volume, but the dry steel erection on site only took 9 months, very fast. And so typically when you put up a steel frame on site, you're going to build in two-story layers across the entire site horizontally. So you build one two-story layer, then you build the next two-story layer on top of it, and so on. But this building was built not in horizontal slices, but in vertical slices. So one complete structural bay, the columns, the gerberettes, the tension tie-downs, and the floor trusses is built in a vertical slice for the whole 12 stories. And then you move down the site and build the next vertical bay, the full 12 stories. And this could all be done without any scaffolding. So here you see one of the columns on its base, which is going to fix to the site cast concrete foundation. And then you see one of the joints in the columns. So the 12 stories are made up by 3 pieces of steel tube. So the construction sequence is that the columns are assembled first, and then the gerberettes are threaded over the tops of the columns and pinned to the columns. The outer end of the gerberette is then connected to the tension tie down to fix it in place. And then finally, the floor trusses are craned into place. So in this image, you see the column, you see the gerberette that has been threaded over the top of the column. You see the outer end of another gerberette with the tension tie rod. So in the left-hand image here is the outer end of the gerberette. This is a 9-inch diameter solid steel rod that's providing the tension tie down. And then the very outer end of the gerberette is called the Sputnik connection. And this is where the diagonal bracing is going to be connected. In the right-hand image, you see the steel floor truss being craned into place to sit on the back end of the gerberette. And the gerberette is shaped and the truss connection is shaped, and when the truss is placed on the gerberette, there are no bolts, there's no welding, there are no rivets. It's a shaped and seated connection, and it requires no fixing. So again, the structure is erected in vertical slices, moving from one end of the site to the other. Uh, so this here we see the Sputnik connection with the tension tie-down rod is the vertical rod that you see in the image, and then the diagonal bracing gets threaded into the Sputnik. And the diagonal bracing runs the entire length of the two long faces of the building to stiffen this steel frame. So you can see then in the model photograph that on the short ends of the building, where there are no gerberettes or tie-down trusses, in three places across the 140-foot span, a triangle of bracing is extended from floor to floor. So we get one at each end and one in the middle, and this then triangulates the end facades to make the entire structure rigid. The floors of the building are precast concrete elements, and these are not precast in a factory. They're actually precast on the site, on the ground. And so each panel is 36 feet long. The columns are 36 feet apart and 18 feet wide. And so these are precast on the ground. After the concrete has cured and reached its full strength, they're craned into place and they sit on the trusses. So you remember that the trusses have two top chords, and so a precast concrete plank or floor panel can sit on each chord of the truss. Once the panels are placed, the formwork is stripped and taken back to the ground, and more panels are cast. So clearly, there are multiple pieces of these reusable forms, not just one formwork to do the whole building. So those are the primary structures, and then there are a series of secondary structures that are literally hung off of the primary structure. So what you see in the left-hand image is the structure that's going to support the escalators on the face of the building. The escalators come to site fully fabricated and are simply craned into place. So where is the skin of the building? The skin of the building is a single glazed skin. So this was built in 1970 before people got worried about energy consumption. And so we have a single skin of a fully glazed building. The structure of this building is both inside the glass and outside the glass. So in the left-hand image, you can see the column, the gerberette, the tension tie-down rod, and the beginning of the floor truss, which bears or rests on the back end of the gerberette. So the yellow elements then are the enclosures. The yellow tube is where the escalators will go, and these are the horizontal corridors that people walk along, and then they become diagonal tubes for the escalators. And then the vertical yellow trusses on the right-hand side of the image, just inside the columns, are where the glass will go. So the glass will be on the inside of the trusses. The trusses then are on the exterior of the building. So most of the structure is outside the glazing, and so it's exoskeletal. And because it's outside the glazing, it's not going to have to be fire protected. So what we see on the exterior of the building is actually the steel itself. The floor trusses inside the building have to be fire protected. But before we see what that looks like, in the right-hand image, then you see the vertical trusses that span from floor to floor, and the glass will be on the interface of the trusses, just behind the trusses. The trusses are outside the glass. So the floor heights here, you remember, are 21 feet floor to floor. And so what these vertical trusses are doing is they're not holding up the building. They have nothing to do with the primary structure of the building. They are actually providing wind bracing to the glass envelope. So the floor trusses are inside the building, and they have to be fire protected. So they are wrapped with this white mineral fiber blanket that you see in this image, and then with a thin sleeve of stainless steel cladding. So the trusses are exposed and visible inside the building, in the completed building, but what you see is not the truss itself. You see the stainless steel cladding to the truss. And the mechanical services are expressed on the outside of the building. So this is not a construction photograph. This is a completed building. The mechanical services are very brightly colored, and they're highly visible on the back facade of the building. And you see then the context of the building, which is a historic quarter of Paris with traditional buildings, so it makes a very strong contrast. These mushroom-like elements that you see in the left-hand images and on the roof are the cooling towers, and you can see the scale of these images of these cooling towers um, with the truck in the bottom image. Shows you just how large they are. So again, in this image, we see very clearly the primary structure of the building, this 140-foot clear span that provides all this column-free flexible space, the circulation zone for people on the front of the building, and the circulation zone for services on the rear face of the building. And here you see then the building in its context in Paris. It is in a historic part of Paris with 5-story load-bearing stone and brick buildings. And you see that it is quite a daring intervention. It epitomizes the tectonic or frame idea of architecture as opposed to the load-bearing, solid, structural walls of the historic fabric of the city. You can see that the scale of the building is quite large compared to the historic context. So whether it succeeds in being anti-monumental, you can decide. But what I would say is that the building, although it was very controversial at the time it was being built, has been wildly successful. It has attracted more millions of visitors than ever anticipated. And so the second building in this sequence is the Sainsbury's Centre in the UK by Foster Associates. And this was completed in 1978, just 2 years after the Pompidou Centre. So Foster and Rogers and their 2 wives had a practice together for a while called Team 4. And then they eventually split up, and each architect went his own way, and they founded their own practices. And so this building is done by Foster Associates, not by Foster and Rogers, but just to say that they know each other, they're good friends, and they went to graduate school together, so they have, a common or shared way of thinking about architecture. So this is called the Sainsbury Center, and it is a gallery for an art collection which was donated to a university by the Sainsbury family. So Sainsbury's in the UK is equivalent to Wegmans here. It is a huge chain of supermarkets that has made the Sainsbury family extremely wealthy. They gave their art collection to the university with the requirement that it should be housed in a building which would also include the art history department of the university. They wanted students in art history to be surrounded by art in their daily lives and not to have to go always to a museum to see art. So happily for Foster's, this was a straight commission where the client contacts the architect and asks them to design a building. It was not a competition. The program for the building is again a hybrid program. So it includes the gallery or museum for the art collection, the art history department of the university, which includes faculty offices, a library, and student lounges, and a public restaurant. So it's a complicated program, and everybody assumed that because of these different demands of the different buildings, that there would be somehow separate buildings that might be linked together. But Foster felt that the interrelationship between art and the students that the client desired were so strong that everything had to be under one roof. And so that is what he has done. One critic at the time said that the building was a very bold move to combine these very different programs together under one roof, especially when the inhabitants of such places are so neurotic. Add to this the clutter and bustle of a restaurant and a student lounge, and you have the ingredients of real trouble. But it works amazingly well. So the site, and that was a quote from the critic. So the site is the University of East Anglia. This is a new university that was built in the 1970s outside of the city of Norwich. And so it's a little bit like our North Campus, built outside the city on a greenfield site. The other buildings of the university are all 5 or 6-story brutalist concrete buildings, and they are all linked together by high-level walkways. So the Sainsbury Centre, you can see then in the foreground of this aerial photograph, is a very different creature. It is a single building that is 110 feet wide. It is 400 feet long and 35 feet high. So essentially, it is a generous double height space that is the size of a football field, or a little bit longer actually than a football field. The plan of the building is deceptively simple. The program is organized in a series of slices along the length of the building. So the diagonal that you see on the right-hand side of the image is the elevated walkway that enables people to enter the building at the upper level and then to descend down to the ground on a circular staircase. And so that entire bay is the entrance at the ground level and at high level. So to the right is gallery. Then you have the entrance bay and more gallery. Then an enclosed, glazed, a large room where the reserve collection is held, where students can study the reserve collection. Then a band of faculty offices for the art history department, which have glazed fronts looking out into an open plan library space, another band of faculty offices also with glazed fronts, then the restaurant kitchen, and then the restaurant itself. So this very complicated program now has been maneuvered into an apparently simple plan. And you can see that the 110 feet span of the structure in the gallery is column-free space. And within The section of the building then, the section at the bottom drawing, you can see it's a double height space for the full length of the building. And within this double height space, there are two mezzanine structures. So over the reserve collection and the faculty offices, and then over the faculty offices and the restaurant kitchen. So these mezzanines are the student lounges then, which are at an upper level. The bottom plan is the drawing of the basement. So you can see the outline, plan outline of the building above, and you can see that the basement is simply a narrow spine which services the building. So the truck dock, the trucks reverse down to basement level and deliver into a long corridor along which there are a series of elevators that take food up to the restaurant and art up to the gallery. So the structure of the building was always going to be 110 foot clear span, and so we have a concrete slab on grade for most of the building, and then this 110-foot clear spanning structure above, which is a steel structure. So the first scheme for the building was this one, which was W section portal frames. And so these are very deep, big sections, big W sections. They're 36 or 40 inches deep, and the column and the beam are welded together at the joints to make a portal frame. And they looked at two options for the skin, one with the skin outside the structure and the other with the skin inside the structure and the structure outside the building. So the image on the left is the development of this structural idea. You see the steel portal frame, the W sections. Then you see on the outside of that, the zone with all the holes in it is a zone for services, and then the weatherproof envelope will be on the outside of that. So all of the structure and services now are contained inside the building. So this scheme was developed, they did a full set of construction drawings, and they were just about ready to go out to bid, and Foster said, stop. This is not right. And he felt that the structure was too muscular, it was too visually heavy. The structure was an obstacle to the distribution of services. That tight services zone on the outside of the structure was very difficult to access and service. And so very late in the day, they changed to a completely different scheme, which is the scheme you see on the right. So this scheme then, instead of W-section portal frame, has triangular steel trusses. Again, it's a column and a beam structure. Both are triangular in plan, and this structural zone now is about 8 feet deep. The weatherproof envelope is still on the outside of the structure, and then on the interface of the structure is a layer of adjustable louvers to manipulate daylight. This structure now and skin arrangement has many advantages compared to the original plan. One is that this 8-foot thick zone can house all the enclosed rooms required in the plan, like toilet rooms and kitchenettes and dark rooms and so on, so that the space in the center can be entirely without enclosed rooms, can be entirely open plan. The 8-foot thick structural zone also houses all the mechanical plant and services for the building. And, uh, and it is very easy to thread services through the trusses, uh, which now are very light and very delicate visually, not visually heavy and obstructive like the portal frame. And so the skin now, the structure is contained between the waterproof skin on the outside and the louvers on the inside. The structure is visible, but it is much less muscular and aggressive. So this then is the detailed development of that model. On the left is the architect's conceptual sketch about how this thick zone around the outside of the building houses both structure and services. It also allows daylight into the gallery. And then on the right, you see the more developed drawing. So the enclosed rooms of the plan are housed in the thickness of the structure at ground level. The mechanical plant is placed at the upper levels, and then at roof level, across the thick roof of the scheme, there are maintenance access ways, catwalks, so that the lighting of the gallery can be totally rearranged and maintained from above. So this zone then houses all the structure and all the services, and the weatherproof skin is on the outside of the structure. Here you can see a three-dimensional drawing of the structure, so you see that the columns are triangular in shape, and the beams are also triangular in shape, and they are diagonally braced. So in the building plan, the triangles that you see down each long side of the plan are in fact the columns. So this is a post and beam structure. The posts are triangular trusses and the beams are triangular trusses. The roof trusses are not flat, they are slightly cambered, so it's 6 inches higher at the center of the span than at the edges of the span. And this is for two reasons. One, to provide a slope to get rainwater off the roof, and two, it is a visual correction to counteract the illusion of a sag with the horizontal roof. So our eyes have a correcting lens in them, our eyes and brains, and so even though this roof is slightly cambered, we perceive it as a straight, flat roof. Within this two-story high volume then are two site-cast concrete structures, which are the mezzanines. These have to be site-cast concrete because they have to be fire protected. So the steel structure here of this double height space is essentially only supporting the roof. And the building regulations say that if you have a steel structure that is only supporting a roof, it does not have to be fire protected. And so the steel in this building is inside the skin of the building, and it does not have to be fire protected because it is not holding up any upper floors. So the two mezzanines are on site cast concrete structures, um, which you see here. The reserve collection with the student lounge above is one of those mezzanines. So this photograph is taken within the roof trusses. You see the maintenance catwalks where the electrical lighting can be moved around and bulbs can be replaced, etc. And you can see that there are actually on the roof two layers of adjustable interior louvers, one at the top of the truss just inside the glass and one underneath the roof truss. So there are two layers of louvers here diffusing the light. From the gallery below, this is what the roof looks like. So you see the light diffusing louvers, and you also see the trusses. But the components of the trusses are steel tubes, absolutely standard steel tubular sections. They are very delicate in cross section, so the structure, even though it's 8 feet thick, is visually extremely light. The mechanical services for the building, then, the servicing strategy for this building is that there is no central mechanical plant room. All the mechanical equipment is housed in this 8 foot thick zone along the two long sides of the building, the full length of the building. And so there are small fan and air handling units along the whole length of the building instead of one central mechanical plant room. These are totally visible from inside the building. Here we're looking out through the louvers to see the fan units. We see the circular nozzles where air is delivered internally, and looking at this, and then if we look at the same thing from the outside, we can see the mechanical equipment very clearly, and we see the black circles are louvers, which are the air intakes. So no central mechanical plant room. This building is not air conditioned. It is mechanically ventilated. And the height of the interior space, this 35 feet interior height, provides stack effect ventilation. So hot air rises, it can then be exhausted out of the building, and this helps to keep the building cool without air conditioning. The construction of the building, then, there's very, the site cast concrete spaces are quite modest in compared to the steel volume. We have the concrete servicing spine at basement level, a concrete slab on grade, and two site cast concrete mezzanines within the building. And that all takes time. It is wet trade on site. So same as the Pompidou Center, while that is being done on site, the steel is being prefabricated in workshops, and it will be trucked to site. So each column comes to site fully prefabricated and simply needs to be craned into place. The roof trusses come in two pieces per span on two different trucks. And then a movable gantry at the center of the span is where the welders sight weld the two pieces together. And then that gantry moves down the space to make that central weld. And the erection of the steel then on site is very fast because it has largely been prefabricated. So in this photograph, you see Foster on the left as a young architect, and he was very friendly with Buckminster Fuller toward the end of Fuller's life, and he collaborated with Fuller on several projects. He was very interested in Fuller's ideas, and particularly the question, how much does your building weigh? Which was a question that Fuller asked a number of very famous architects, and none of whom could give him an answer. He thought that the weight of a building was an index of its environmental credentials, and that the lighter we could build, the better in terms of inhabiting the planet responsibly. So Foster and he exchanged letters about the Sainsbury Centre, in which Foster sent him this drawing saying that the Sainsbury Centre was equal in weight to the ship that he drew below, but it contained a much greater volume of space, and so was much more efficient use of material to enclose space. The cladding for the building, which we will study in more detail in a couple of lectures down the road, is a very innovative system. The same cladding system is used for both the walls and the roof of the building. The entire building has one panel size and 5 different types of panels. So you see a solid metal panel, a louvered metal panel, and a glass panel. Those are the 3 flat rectangular panels. And then to make the curved connection between wall and roof, there is either a curved glass panel or a curved solid panel. These panels are totally interchangeable and movable. The panels are a thin layer of aluminum bonded to rigid insulation. And then the end walls, and so here you see the panels on the cladding panels on the outside of the trussed columns and beams. The end facades of the building then, because this is an open-ended tube of space, the ends facades are totally glazed. And so these were the largest pieces of glass ever fabricated up until that time. They're 25 feet tall by 8 feet wide, which you see here. So the fully glazed end of the building, 25-foot tall pieces of glass, and these are hung from the trusses above. So this is a suspended glazed wall, and so this is, you might actually say, a curtain wall. So you can just see in this image that there are glass fins at each of the vertical glass joints, and the glass fins are perpendicular to the glass wall. They go from floor to roof truss, and these provide wind bracing. These are inside the glass, and these provide the wind bracing for this glazed facade. There are no metal mullions, it's frameless glass. The joints between the glass and the fins and the glass panels are made by clear caulking. So then here you see the impact of the glazed ends of the building, which are very transparent. This is the gallery end of the building, which looks out over the lake, and the other end of the building, the restaurant, has the same facade and looks out to the woods. So comparing these two buildings, the Sainsbury's Centre is clearly more restrained, more classical. The Pompidou Centre is more Baroque, more expressive, letting it all hang out. And it's not to say that one is right and the other is wrong. It's to say that the two architects involved, or the architectural teams involved here, have very different aesthetic sensibilities. Then if we look at a third example, the Waterloo International Terminal in London by Nicholas Grimshaw was completed in 1993. So this was the last building, or the most recent building in the sequence. So this was designed as the terminal for the trains that would be running between London and Paris in the new Channel Tunnel. And so the Channel Tunnel was providing some competition to the airlines, and they wanted this terminal to have a very strong visual image to compete with the airports. And so in this aerial photograph, you can see the terminal. So you see the River Thames, and then the Waterloo train station is on the south side of the Thames. It is a major train station for London, and it was built in the early 1900s, so it's been there for over 100 years. The international terminal is the caterpillar that you see on the leaf. And you can see that the site is very tight. It's a dense urban site. There's no space around the building. It is curved in plan. It tapers, so it's wider at the east end and narrower at the west end, and it also slopes. So it's a curved, tapered, and sloped site in a very dense urban setting. So this provided a lot of challenges in terms of the geometry of the building. And again, in this building, there's a very close relationship between the architectural space, the structure, the skin, and the enclosure systems. So then what we see is that the scheme is resolved in section. And so we have a site cast concrete structure that provides 2 and 3 stories of accommodation with the train platforms then on the roof of the building. So this is an international train station, and when people travel from here, they have to go through passport controls, etc., like an airport. So that all happens on these lower levels, and then people go up to the platforms on the roof to catch the train. The concrete then in this building, and then you can see that the roof over the train platforms is the steel structure. So that's what we're going to be looking at in detail. But just to say that the concrete is 90% of the cost of this building and the steel just 10% of the cost of the building. And yet the steel roof of the train shed is the entire total public image of the building. So on the lower floors, where you have the concrete structure, you have columns at regular spacings. But up on the train platforms, then, you get a clear spanning structure of column-free space over the trains. And so this structure is an interesting study in repetition and variation. Because of the curve and the taper and the slope of the site, no 2 bays of the roof structure are the same. And so likewise, the section of the roof, as you can see, the structure is a 3-pinned arch. So there are 2 pins, 1 at either side, and then not in the center of the arch, but asymmetrically at about the 1/3 mark is the 3rd pin. So the structure is asymmetrical. The structure on the left-hand side of the section is different than on the right-hand side of the section. And then as you move along the length of the building, the site tapers and slopes and curves. So the span here, this clear span from side to side of the arch ranges or varies from 100 to 150 feet. So this is very different from the Pompidou Center and the Sainsbury Center, which are both absolutely repetitive sections. So once you have one bay of structure, you simply repeat it over and over to get the entire building. Here, each bay of structure is slightly different. So the structure here is comprised of triangular trusses which are triangular in section, like the Sainsbury Centre that we just looked at. Uh, but the Sainsbury trusses, again, along their entire length, are the same depth. These trusses are banana-shaped, so they're triangular and they're banana-shaped. They are deepest at the center of the span, where they have to deal with bending, and then they taper at each end of the span. And like the Pompidou Center, if the elements of the trusses that are working in compression are hollow steel tubes, and the members that are working in tension are solid steel rods. And so the impact then of this structure visually, you see the concrete levels below the train platforms here, the 2 and 3 stories of facilities below the platforms, and then you see this rather dramatic and elegant steel structure over the train platforms. So then this is the structure in section, but you can see then what it looks like in plan. And so you see that the trusses are banana-shaped in both section and plan, and they are triangular. So on the long side of the three-pinned arch, the banana shape has 2 compression members on the top side of the truss and 1 tension member on the bottom element of the truss. And then on the other side of the building, that flips over, and the compression members are on the bottom of the truss and the tension members are on the outside face of the truss. So tension and compression members flip-flop on either side of the three-pinned arch. On the long side of the arch, then the structure is inside the cladding, and the cladding is corrugated metal. And in this drawing, it shows that there were proposed to be roof lights over the banana trusses. That did not happen, and the entire roof is corrugated metal. Then the short side of the three-pinned arch is fully glazed. So here then you see that three-pinned arch more closely. And so every one of these trusses is a slightly different shape. And they had the problem of saying, how do we fabricate this? They wanted the compression members to be larger and in diameter, and because they have to work harder at the center of the span and to taper at each end. So the compression members would taper just like the banana tapers. But to build that, to fabricate that, would be extremely expensive. So the system that they devised is to use standard circular steel tubes of 3 different diameters that fit inside each other. And so the compression members of the trusses telescope out of each other like the legs of a camera tripod. And this telescoping does not occur on site. It happens in the fabrication works, where each truss is very carefully fabricated to its precise length. But the beauty of this is that they can fabricate these unique trusses using all standard circular steel tubes. So this makes it very affordable. So on the left-hand image, you see the long side of the three-pinned arch with the banana trusses inside the metal cladding. And on the right-hand side, you see the short side of the three-pinned arch with the trusses now outside the glazing. So the glazing will be just inside the trusses. So half of this building then has an exoskeletal structure with the structure outside the skin, and on the other side the structure is inside the skin. And in the right-hand image, if you look at the heavier compression member of this triangular truss, you can see that it is fatter at the middle of the span, and then the smaller diameter telescopes out from that, and then the smallest diameter is at the ends of each compression member. When the trains come this complicated section then is achieved using standard components. Here then you see the impact of the structure and the cladding visually. You see the sinuous curve of the space, and it's quite striking visually. When the trains come into the shed, these are high-speed trains. They're very long. They generate a lot of wind inside the shed. And so this glass skin has to be able to move so that the glass panels don't break. And so in the right-hand image, you see some of the movement joints between the overlapping, basically what are overlapping glass shingles. They're very large glass shingles. And those overlapping joints have rubber gaskets so that the glass can move without breaking. And then you see here an accordion joint between panels of glass and a kind of roller connection, all of which are designed to allow for movement. And the new end wall to the existing terminal is a fully glazed wall that is in which the glass is held by cable trusses and point fixings. So there's no metal mullions. And you see in the section to the left, the straight line in the middle is the glass, and then there is a cable in tension both inside and outside the glass. And you need both cables because sometimes the wind pushes and sometimes it pulls. And so you need to have a cable that will go into tension in both of those situations. And this is a frameless glass wall, no mullions. The glass is held by what we call spider fixings or point fixings that then provide also the fixing points for the tension cables. And the tension cables here, the cable trusses, are wind bracing this glass wall. And so here you see the impact of the on the short side of the three-pinned arch. The glazing is inside the structure. The structure is exoskeletal on that side. Then it flips over, and then the steel trusses are inside the metal cladding on the other side, on the longer side of the shed. So, Waterloo International Terminal is a long span structure ranging from 100 to 150 feet, clear span. This is long, but it's not huge. It had been done before in the 19th century. Curved train stations were built in the 19th century, but the complex geometry of this site made this project very difficult, with potentially every bay of structure and every piece of cladding a unique size and shape. And so through careful design, a way was found to use standard steel tubes, standard steel circular tubes, to achieve this variable structure. And the complexity of this structure and skin system was made manageable through the use of the computer. So this building was designed and fabricated just as computers entered the workplace in a big way, and the software that was being used enabled this very complex scheme to be both made economic and buildable. So that finishes the lecture for today. We'll see you for the next lecture.